Hello everyone! In this video we will introduce topic D.3, Cosmology. Cosmology is known as the study of the origin and evolution of the universe. So how the universe came to be and its beginning, and how it has changed over time. And our central question for our study of cosmology will not in fact be sort of exactly what has happened over time, although we will certainly talk about that, but we will most centrally ask, how do we know? Virtually everyone at this point has heard of the Big Bang and Big Bang theory. And our main question will focus then on how we know, why do we think there was a Big Bang? What do we mean by the Big Bang? And how could we possibly know what has happened over time? Often, cosmology will be depicted with graphics that look like these two right here. And we'll talk about sort of different eras, different time periods as we go along. And most of them are shown with this sort of logarithmic scale. As you can see, up to the present day over here, it splits up the history of the universe, or cosmology, into different eras and different things that happen. And most of the exciting stuff happens right at the beginning. So there's a logarithmic scale that shows that as it goes on. And we'll go over several of the events depicted on these graphics. So, to set the stage for the study of cosmology, it's important to recognize that we think of the science of cosmology in many ways as beginning in about the 1920s. Because up to that point, people believed the following. They believed that the universe was static, so unchanging, staying the same more or less over time, infinite, so without end in any direction. There was no reason to believe it was somehow limited, eternal. So the idea was at that point that it had existed more or less as it is forever, and would exist forever, whatever that means to different people, and homogeneous or homogeneous. This implied that there was an even or roughly even distribution of matter. And together with these assumptions, though, so these were the background assumptions of almost everybody, this was already problematic. So this set of assumptions was already problematic, and Olber is somebody who articulated this problem in asking sort of why the night sky was dark. He looked up at night and said, well, if the universe is static and infinite and had an even distribution of matter and eternal, so there's been an infinite amount of time, why is it that we can't see a star literally everywhere you look? He said, well, if I look up at the sky and I just point in a random direction, if the universe is truly infinite and there are stars spread evenly throughout, then anywhere I point, I should end on the surface of a star. And therefore, the night sky should be infinitely bright. This can be made mathematical, but this statement of it is known as Olber's paradox. And so even up to this point, people knew that something was fishy in this set of assumptions, that something couldn't be the case. So one of these assumptions was flawed, or more than one. And this included Albert Einstein, who is very famous for giving us our best theory to be used in cosmology. General relativity governs the equations that determine what happens over time. And as we've discussed before, those equations relate sort of matter and energy, which is this term over here, to space-time, to the rest of space-time. But in Einstein's original formulation of what are now called the field equations, he included an extra constant. And that constant, known as the cosmological constant, was thrown in there to preserve the static universe. It's not that it wasn't allowed. It's allowed by the equations. But it's kind of like, for those of you who've taken calculus, choosing your plus c to be exactly the right value. And he threw it in there in order to preserve the static universe, to preserve a universe that would be largely unchanging. Because he saw that left unchecked, gravity would mean that the universe would collapse over time. And so this concept actually came back in a major way, as we'll discuss later on in cosmology. But the general point is that up to this point, up to about the 1920s, everyone understood the universe to be static, infinite, eternal, and homogeneous. In the 1920s, Edwin Hubble measured the radial velocities of nearby galaxies. Are they moving towards or away from the Milky Way? And his major discovery was that virtually all galaxies were redshifted, to be explained in the next video, and therefore moving away from us. Every single galaxy nearby and further away, although we could only measure the nearby ones, was moving away from us. That was remarkable. But not only that, the redshift, or their velocity, was proportional to the distance away from us. So how far away they were was proportional to their velocity. The farther away they were, the faster they were moving. We will consider sort of the ramifications of this, as well as explaining the concept of redshift in the next few videos.